welcome and thank you for joining. Let's take a look at an application of derivatives question, and more specifically, this is an optimization word problem that requires the use of derivatives. So we're going to start off by reading the question first. A trough can be made to the dimensions shown. So we are given some diagrams in here. So remember first you read the question just to get a general idea of what it is about. Only the angle theta can be varied. Oh, wait a second. Where is angle theta? So I see angle theta right here. So this is the only quantity that can change. Now we want to find out what value of theta, so what would be this angle, so that the volume becomes a maximum. Your answers must be in exact form. Well, that's good to know, and keep in mind at towards the end of the solution. And you must show how you use a second derivative test to find the maximum. So be careful with this because there must be at least 2 or 3 marks if you have a question like this on the test. So it would be 2 or 3 marks to determine the second derivative and then estimate the derivative at the indicated point. So as I said, you read the problem first and then you try to read it the second time, but connecting the diagram with the information given more carefully this time. So as you can see, we are given a trough, which is basically a prism, a 3D shape, and the cross-sectional area of the trough, which serves as the base of the prism, is a trapezoid. So this trapezoid is right here. You can see it's the same trapezoid that fits in here. And as you can see here, we have a trapezoid with sides that are equal to each other. So this is 2, 2, and 2. And only angle theta can be changed to maximize the volume of the trough. Now, as you can see in here, we're not talking about the depth of the trough, which serves as the height of this trapezoid-based prism, which means that the volume of the trough will depend on the maximum, on the area of the base. So whenever the area of the base is a maximum, so for whatever theta area of the base becomes a maximum, then the volume will become a maximum. So that will simplify the solving process because we will not have to consider this 20 meters, and like we can, but that will just make the coefficients in the equation bulkier and bigger. So let's get to work. So our focus now is this trapezoid with sides equal to 2 meters. One of the bases equal to 2 meters is an isosceles trapezoid, we call it, because both sides are equal, right? Non-parallel sides are equal. And we need to maximize the area just by changing the angle theta. Now, I want you to imagine that if the angle theta here becomes a very small, like closer to 0, you can see that the area of this trapezoid will decrease significantly. And if the angle theta becomes exactly 0, then we won't have a trapezoid. So we would have this 2 meter side go right here, and we won't be able to build a trapezoid. So if theta equals 90 degrees, again, we don't have a trapezoid, so we create a square in here. So we don't want to do that as well because we want to maintain the same shape of the cross-sectional area because it's a trough, right? That's how they are made, with the trapezoid bases. So since we're trying to maximize the area, then we should get started with the formula for the area of the trapezoid. And I'm going to draw the diagram one more time in here so that I can explain in more details to myself and in a bigger diagram. So what I'm given and what I'm trying to find. So what we are given here is a trapezoid that measures 2 by 2 by 2. And the angle theta is the angle that I have the power to change. So as you can see here, this angle theta and this angle here would be the same. So, it is in our best interest to bring angle theta inside the trapezoid so that we can use it to determine the different measurements in it. So similarly, this would be theta as well. So in order to determine the area of the trapezoid, we're going to need the length from here to here. This is one of the bases. This is the other base. So we're going to need this length as well, and we're going to need the height. So let's fill this diagram in with more information. So we're going to let the side from here to here be x, and as you can see, from here to here will also be 2 meters. And this will make the base b, which in our case will be 2 meters, that's 2 meters, plus x plus x. Then the next thing that we need to take care of is the height. So we need the height of the trapezoid in order to determine the area of it. So the height of the trapezoid, I'm indicating this in green color, would be this one here, and this one here as well. Now, please do not assume that the height is equal to 2 meters. That is not necessarily true, okay? So because the trapezoid can stretch very wide, all right, or it can stretch as tall as it can, right? So height is different than 2. And it's an assumption that people make very often, from what I've noticed whenever we discuss this problem in class. All right, so let's get to work. Start off by writing the formula of the area of the trapezoid. And now we have to determine, we know the A value, and we need to determine the value of B. Now the value of B would be 2 plus x, so 2 plus 2x. Now, in order to express the area of the trapezoid in terms of theta only, then we need to express x in terms of theta. So when you look at this triangle right here, which is a right angle triangle because the height is perpendicular to the base, then we can tell, or we can see, that x divided by 2 will be the cosine of angle theta. So that tells us that x equals 2 cosine theta. So using this, then we can find the value of b as 2 plus double of x, which is 2 cos theta. And in a more simplified form, we'll say that b equals 2 plus 2 times 2, 4 cosine theta. So in a similar way, we'll determine the height. So the height is in the same right angle triangle here, is located opposite to angle theta. And the hypotenuse is 2. So that means that we can build the ratio h over 2 equals sine theta. So opposite over hypotenuse equals sine theta SOH. So which gives us h equal to 2 sine theta. So now that we have the values of b and h, we can start substituting into the area of the trapezoid formula. And before we start solving, let's bear in mind that the angle theta has to be greater than 0 and less than 90. So if the angle is 90, we no longer have a trough with a trapezoid sectional area. And if the angle is 0, we don't have any 2D shape, okay? So let's substitute into the area formula. So the value of A is 2. The value of B is 2 plus cosine theta. All of it is divided by 2 and multiplied by height, which is 2 sine theta. So we'll simplify the formula before we differentiate. So notice that 2 and 2 will simplify, and that will give us the area in a more simplified form as 2 plus 2, 4, plus 4 cos theta times sine theta. And in this case, then, we would say that the derivative dA d theta would be, remember that here you have a product rule, derivative of 4 plus 4 cosine theta, which is, derivative of 4 is 0. 4 cosine theta would be 4 times derivative of cos is negative sine, and then multiplied by sine theta. So this would be the derivative of the first factor, and then multiplied by sine theta, and then plus the derivative of sine, which is cosine, multiplied by 4 plus 4 cos theta. So this would be the derivative. Next, we will simplify it. Negative 4 sine squared plus 4 cosine theta plus 4 cos square theta. Now, it is in our best interest to express the derivative in terms of cosine only, because we know to find the derivative in this case means to find the optimum, I should say, means to make the derivative 0. So the optimum value will happen at wherever the derivative is 0. So 4, replace sine squared by 1 minus cosine squared plus 4 cos theta plus 4 cos squared. That will give us, in a more simplified form, 4 plus 4 cosine squared theta equal to 8 cosine squared theta plus 4 cos theta minus 4. So what we are going to try to do to find the optimum value is set this equal to 0, because we know that the max and the minimum value of a function always happens wherever the derivative is 0. So that will create the equation 2 cosine squared theta plus cos theta minus 1 equals 0. Remember, in an equation, we can reduce the coefficients. It makes solving the equation easier. Now let's get to work. We have a trig equation to solve, so we are going to solve by factoring 2 cos theta minus 1, cos theta plus 1. So basically, you start with cosine theta here. We have a coefficient 2. The only way to break it down is into factors 2 and 1. And we need two numbers that multiply to negative 1 and add to a positive 1. So that would be negative 1, positive 1 in here. And as you can see, positive 2 minus 1 would be equal to 1. So make each factor equal to 0. And that will help us find the values of theta for which the derivative is 0. So cos theta would be 1/2, so take negative 1 to the other side, which suggests that theta equals inverse cos 1/2, which is theta equals 60. And similarly, cos theta equals negative 1 here, which gives theta equal inverse cosine negative 1, which gives theta equal to 180 degrees. So as you remember from the beginning, we said that theta has to be between 0 and 90. So let's take a look at which solutions are valid. So 60 is between 0 and 90. So this is the value we need to check and see whether it's a min or a max for our problem or our trough. And theta equals 180 is automatically rejected solution. Because theta cannot be 180, we won't be able to build a trough in this case. So we have arrived almost to the end of the solution, so theta has to be 60 degrees. Now it's time to do the second derivative test, and remember this is in exact form. So the second derivative test suggests that we use the second derivative to prove that whether the critical value that we found was a min or a max. And the way this works is by first finding the second derivative. I always like to start off by writing the equation of the first derivative, because yes, it is a little bit more writing, but it provides more accuracy and more confidence in the solution. So we'll say that the second derivative would be, so remember that we have the sum of three different terms in here. So 8 cosine squared theta, you have a little chain. So coefficient 8 stays in here. We do the power first because this is like cosine theta to the power of 2. So the outside function will be the power function. So that's 2 cosine theta, and power here would be 1 for cosine. And then the inside functions, cosine has the derivative negative sign. Now the next term is easy to differentiate for negative sine theta, and we want to clean it up and write the equation of the second derivative in a more simplified form, and don't forget to evaluate it at 60 degrees. So 16 with a negative sine times cos minus 4 sine theta. Now let's take a look at all the signs in here. So as you can see, we have a negative 16 in here. We have the sine of 60 and cosine of 60. That's what we are substituting. And then we have minus 4 sine of 60. So what that means is that for sine 60, we know that we have a positive number, and same for cos 60, because 60 is in the first quadrant, and in the first quadrants, all ratios are positive. And sine 60 again here is positive. So as you can see, we have the product of a negative with two positives. So this entire thing in here will be a negative. And oops, I'm going to make it more dramatic here. And we are subtracting a positive. So this is another negative. So when a negative is added to a negative, it means that the answer will be negative. So what does that mean in terms of second derivative test? So when the derivative of a function, second derivative of a function, is negative at a point, it tells us that the function must be concave down at the point where we evaluated the second derivative at. Now, since this is not just any ordinary point, this is a critical point or a turning point, it means that this point will be right here on top. So that will mark a maximum for this function, and this is how we prove that at angle theta equal to 60, we'll have the maximum area of the trapezoid, so of the base, which will provide the maximum volume of this trough. Well, thank you for learning with me, and I hope this made sense. Bye for now.